Hello, my dear students. Warm welcome to all of you. We are with physics now. Okay, we'll be talking very seriously about physics now. Okay, myself is Dr. Shobboshachi Shen. I'll be offering you the physics courses, course objective, course outcome. You can see on the screen, and we are in outcome-based education. So every course is mapped with what is its probable outcomes, which I have illustrated later on. Now there are five modules. Now we'll be adapting one by one to each module and explore the world of physics. Now let us explore what is the topic of the day. You should keep one thing in mind, that whatever we teach in these classes, each video lecture is basically a building block of your future engineering courses. Each class is going to give you some fundamentals, some new concept. And if you add all those concepts at the end of the semester, you will get the correct path of entering into your own engineering curriculum, because all your curriculum are essentially the application of physics. Engineering means physics applications. So let us explore it a bit more. Hello guys. Good morning to all of you, and warm welcome to my class. It's 28th class in a row in our course on Physics 1. 28 class is a very long journey. We have made a very long journey of 28 classes, and we came across so many topics, starting from the basics of quantum physics to the study of lasers, optical fibers, a bit of classical optics, interference diffraction, and now we are busy with the studies of solid structure. We are talking about solid state physics. I have taken already two classes on the elements of crystallography, the basic idea about what is space lattice point, unit cell, and next class was about various types of unit cell, related parameter calculation like atomic packing fraction, coordination number, effective number of lattice points inside a crystal, particularly three Babbage lattice we consider: the simple cubic crystal, body-centered cubic crystal, and the face-centered cubic crystal. Today, we'll move forward with some more information about crystallographic structures, and we'll mainly talk about in each two topics. One is the how you define a point in a crystal, that is direction in a crystal, and also the how you define atomic crystallographic planes. Okay, so the main objective of the class is to talk about how you assign or define crystallographic planes or each surfaces of a crystallic structure, and also we'll end up with Bragg's law of X-ray diffraction. So after ending the class, you'll be able to explain how you define any plane inside a crystal. Okay, all this, and also how the crystals are used for the diffraction of X-rays, because there is something we have already applied in division jammer experiment when we compared Bragg's law, where X-rays are diffracted with the electrons being diffracted also from the crystallographic structure. So you'll be able to explain all those things. So let us get into the business. This is 28th class in a row. This is me. You can contact me in these phone numbers and in these email IDs. Okay. And now you please see, this is very elementary. I have been telling you every day. This is how matters are made of: solid, liquid, or gas. Okay, and in crystallography is more connected with the solid structure. Okay, so two types of crystal structure may be there with two solids may be either crystalline or amorphous. Crystalline means there is a definite arrangement of the atoms or molecules which are making the crystal, or the order parameter is long range. So for a higher distance, the proper arrangement of the atoms or molecules are maintained. And examples of crystal structure like table salt, the sugar, sand, snow, ice, diamond. Okay, all these are the examples of the crystallographic structure. And you can see these are some more examples. Sodium chloride crystal means stable salt. Water crystal, that is uh, ice itself, diamond. Okay, diamond. You see so many good uh, decorated eyes are there. Okay, now in the picture, I'm talking about this picture. And diamond itself is so good. It's a crystal structure. These are the variety of the crystallographic crystalline structure, molecular crystal, ionic crystal, network crystal, metallic crystal, molecular crystal with polar, non-polar, hydrogen bonded. All these things are there. And amorphous crystal means amorphous solid means it does not have a long range order parameter. If any arrangement of the ordered arrangement is also noticed, also it cannot be there for a long distance. Okay, it cannot be there for a long distance. It is within few atomic lengths. It is maintained. Okay. So this is all about the amorphous crystal. Amorphous crystal, maybe this sugar candy. It's an example. It's the glass. Glass is amorphous crystal. So these are the concept of lattice points. Lattice points which are on periodic or repetition after a definite gap called lattice constant actually forms a crystal. Repetition may be along x, maybe along y, maybe along z. This is the concept of unit cell, which on repetition in the 2D or actually which will be repeated in 3D and makes the entire crystal. So that those are the lattice point, and that is a unit cell. Unit cell is defined by three parameters: three lengths ABC, triangles alpha, beta, gamma. Choice of ABC and alpha, beta, gamma will actually classify unit cell. This is a primitive unit cell, okay, where there is, okay, which is just an elementary unit cell, okay, where those basic repetition actually it cannot have a smaller unit cell than this. That is the concept of primitive unit cell. Actually, there are 7 primitive unit cells are there, and they are conventional unit cell. Like the left hand side, that blue balls are there making a simple cubic crystal. Right hand side, you are getting a body centered cubic crystal. The simple cubic is primitive unit cell, body centered is conventional unit cells. So in this way, ideally in a primitive unit cell there may be one effective number of atoms. I have shown you the other day. And when you have to make an actual solid, at every point of the lattice point you have to add the atoms, which makes the basis. For example, those red and blue balls are lattice points now. If you are adding say copper there, then you are making the crystal of this is a structure of copper. Okay, copper is body centered cubic structure. Then those points are called basis points. So these are the 7 primitive unit cells: cubic, rhombohedral, hexagonal is wrong. Okay, it is not the hexagonal structure as I mentioned. Tetragonal, orthorhombic, monoclinic. Okay, all these are essentially, okay. This is not the hexagonal structure. Uh, Yesterday I have shown you. Triclinic. Okay, cubic means all ABC alpha beta gamma are equal. Alpha beta gamma are equal to 90 degree. Rhombohedral means alpha beta gamma are not equal to 90 degrees. Still ABCs are equal. Hexagonal means A equal to B not equal to C. That is okay. These things are right. This statement is right. Alpha beta gamma equal to 90 degree, gamma equal to 120 degree. Okay. Tetragonal ABCs are on A equal to B not equal to C. Alpha beta gamma 90 degree. Orthorhombic means nothing is equal. Monoclinic means nothing. ABCs are unequal. Alpha gamma 90 degree if they are not equal 90 degree. And triclinic ABC are different. Alpha beta gamma are also different. So from these actually 14 probabilities are generated. Simple cubic, you know, there is no other atoms excepting the corner. With body centered cubic, one atom will be at the center of the body, center of the crisp unit cell. Face centered means atom should be at the center of each face. A simple tetragonal is there. Body centered tetragonal you can see. Hexagonal now it is okay. Okay, this is the hexagonal structure. Simple mode orthorhombic is there. Body centered orthorhombic means at the center will be there. Base centered means one at the top and at the bottom. Face centered is also there, but this is not rightly drawn. Atoms should be at the all center of all the faces. Okay, it will be here, it will be here, it will be here, it will be here, everywhere it will be there. Rhombohedral, simple monoclinic, body centered monoclinic, triclinic, everything is there. Okay, 14 probabilities, and this is non-probabilities like the honeycomb structure. Okay, because in a lattice, any atom should have identical points. Okay, so the surrounding of this point and these points are different. Okay, or this point and these points are different. You can realize. Okay, so the idea is this much. Now this is simple cubic crystal. Atoms are at the corners. Coordination now effective number that is 0.1. Coordination number, how much will be coordination number 6, and atomic packing fraction is close to 52%. Okay, body centered cubic crystal, one atom at the center of the body, and packing fraction is 68%, and also effective number of lattice point will be 2, coordination number will be 8. FCC structure, effective number of lattice point will be 4. I have shown you the calculation. The atomic packing fraction is 74%, and the other one coordination number is 12. Okay, this is how coordination number effective number lattice point is calculated. Told you is this is BCC structure. Okay, FCC structure, coordination number 1 2 3 4 5 6. You can see the minimum distance it is maintaining with that orange ball with any other atom. BCC means all 8 are at equal distance because that is at the center of the body. FCC means on the plane 4. You see on the plane, this is on the plane 4. Okay, side of it is 4. Left hand side also it is 4. So 4 plus 4 plus 4 is 12. Okay, this is how atomic packing fraction is calculated. The formula is that the effective number of atoms per unit cell into the volume of the one atom, okay, divided by volume of the unit cell. Okay, so volume of the atoms in unit cell, one of the volume of the one atom is how much? 4/3 pi r cube. Okay, so here 2r will be equal to, it's not difficult. Okay, 2r, this is 2r, r plus r, a is equal to 2r, so r is equal to a by 2, so a by 2 means 0.5. Okay, so it is done like this way. And for FCC structure, you can see s square plus s square is equal to 4s square. Okay, so 4r is equal to, okay, from here on you get the value of r is equal to root over 2a by 4. You put it and calculate atomic fraction. Body centered cubic, same story. The connection is this much. Say 4r is equal to root 3a. You put that value in the expression of 4/3 pi r cube. 2 is the effective number of atoms per unit cell. So it is like 68%. Now, important issue is crystallographic direction. Now, you look at the picture here. Okay, any point here is defined by crystallographic direction. So it's a vector. Okay, like this. Read the projection of, in terms of unit cell dimension ABC. Adjust it to smallest value and close in square bracket and no commas are put. Okay. For example, choose any point. Okay, this point, for example. Here x is 1. This is origin. The x is 1. The y is 0. Y means here. So it is along this line. And z is half. So it is here. So it is defining a point here. So it is represented by, take the numerator, the LCM of the numerator is 1 by 1, 0 by 1, 1 by 2. So basically, the LCM is 2 multiplied. So it is 2, 0 into 1. So this defines any point. Okay. If you choose any other point, okay, the intersection with the x-axis is at -1. Okay, this is -1, y plus 1, so z plus 1. So basically y plus 1 and z plus 1. So this is -1, y plus 1, z plus 1. That means it's indicating this point. Okay. So we take the even the LCM also multiplied by 1. -1 is called 1 bar. So this is how you define the crystal. Any point, in any point in the crystal, you can define like this way. Okay. So more examples you can see here. That was this point. Any point here, how you define the along this is x direction. So along x it has got some value 1, and y its value is half, and z it has got no value. Okay, that means z is 0. So that is the story. You take the LCM, 2, 1, 0 is the direction of this point. So it is put in like this way. So another point you see, x is half, y is half, x half, y half, z is 1. Okay. So if you take the common, it will be like 2 into half is 1, 2 into half is 1, 1, 1, 2. This is the way we calculate actually. Any point you can define. Okay. Even you can, suppose you want to define this point, then how do you define? Its interaction with the intersection with the x is 0. Intersection with the y is 1. And intersection with the y1 and z is, you have to choose nothing but x0, y1. Those z is also, z is half. So this will define this point, okay? So how do you define? These are the intersection 0, 1, half. Now if you take a LCM, this first point remains to be 0. This is 2, this is 1. Now this will define that in this point, okay, this will define the 0 to 1 is the direction of this point in the crystal. Now, apart from only defining a point, a very important idea in crystallographic structure is Miller indices, which does not define a point, rather it defines a full plane in a crystal. Okay, so this Miller indices, suppose this is one plane, this is one plane. Okay, so six faces are there. Each one there is a plane in a in an inside a unit cell. So how you calculate it? Okay, choice of origin is arbitrary. Axis and their sense. Once chosen, cannot be changed. Unit distance need not to be unity. It is distance between two lattice points in a particular direction in its crystal like that. Okay. So now let me show you some calculations of unit cell. The first one is 1, 1, 1, 1, 1. Intersection is that 1, 1 infinity because it is not intersecting with anybody this plane. So the technique is this, as it is written there. First step, you get the intersect. Step 1. Step 2, as you did earlier, you take inverse of them. Okay, that is 1 by 1, 1 by 1, 1 by infinity. Now, you have to take the LCM of them. So LCM of the denominator is 1, obviously. So if you multiply, it is 1 into 1 into 1 by infinity as good as 0, okay? 0. So this plane actually refers to the 1, 1, 0 plane, okay? Another example is this one. So look at this picture. The intersection of the x-axis is here. You see, it is a half or a by 2. So it is half here in the x direction. Y direction, how much it is going? It is also half. And z direction, how much it is going? It is going over. It is half in the x direction. Half, it does not meet with the z axis, okay? And it does not meet with the y axis also. So this is intersection with y is infinity, z is also infinity. So let me show you this calculation slightly separately. Just let me show you few calculations. Okay, these few calculations as they have shown you. This x direction with distance vector A, y direction is given translational vector B. Okay, so this is my unit cell, so vector C. Now this is a plane I am asked to calculate, define this green colored plane. So how do I calculate it? First you calculate the intersection with the three axes. So intercept with x, it is at 1 by 2, 0, 0. Now next is that intersection, where it intersects with the y-axis. Okay, you see it is parallel to the y-axis. This is the y-axis. So basically no intersection. So theoretically it intersects at infinity. Okay, it intercepts at infinity, and it is, you see it is also parallel to the z-axis. So with z-axis also it never touches. So along z it intercepts at infinity. So the intercepts are like this much. Along x it is at half, along y it is at infinity, along z it is also at infinity. So if I take the reciprocal of that, this is 2, this is 1 by infinity, this is 1 by infinity. 1 by infinity means 0, this is 0. So basically this plane is 2, 0, 0 plane. This is the midliness of this plane. Okay, this is the 200 plane. Another example will be like this, but the other case, as I am trying to show you, this is the case I have just shown you, 200. Now let me show you the first case, how it is 110. Okay. Again, this is the unit cell. Okay, then these are the vectors. And suppose this is the point plane I want to define. So its intersection with the x at 100, y is also at 010, and with z it has got no intersection, so it's at infinity. So the intercepts are along x1, along y1, along z, infinity. So we calculate reciprocals 1 by 1, 1 by 1, 1 by infinity. So these are becoming how much? 1 1 0. So this plane is basically 1 1 0 10. So in this way you can do it. You can define any plane as a matter of fact. And another option I am showing you, the third case, is also very easy to realize. Suppose again this is my crystallograph unit cell, and this is again x, y, and z three axis. Three vectors are there. And now I do want to define the plane. Intersection here is 1 0 0, here is 0 1 0, and here is how much? 0 0 1. So intercepts are x axis 1, y axis 1, z axis 1. So mirror indices is 1 1. Sorry, first it is the reciprocal 1 1 1. So mirror indices is 1 1 1. So this plane is the that famous 1 1 plane of the cell. Okay. So this is a way we can define any crystallographic plane. Some more examples are there. You can try 1 by 2, 1, and 3 by 4. Many combinations may be there. Same technique. Okay, it will be the LCM of 2 and 4, which is 4. So multiplied by 2, half, how much it will make? 1 by half means 2. 1 and 4 by 3. So basically the LCM is 2. 2 into 3, it is 6. 3, yes, 4. Fine. Some more examples are there. You can practice yourself. Okay. Okay, just like I was saying this example. So this case is 1 0 0. It is x is 1, y is infinity, z is infinity. 0 1 0. X is 1, y is 1, and z is not meeting 1 1 1. So these are all coming in the discussion. Okay. So these are indicated by a set of those numbers called mirror indices. Now another very important idea in this study, you see this wonderful animation. There is X-ray coming in and incident on the atomic plane, and as a result of that, X-rays are getting deflected, scattered from the atomic planes. Now, after passing through, what the X-rays will do, they will either, as a matter of fact, if light is incident on any surface, three things can happen. A portion of the light gets reflected. I just show you here. Next page. If radiation is incident on a surface, if it is a mirror type surface, this will be all reflected. If it is a glass surface, radiation coming in a portion will be transmitted, should be reflected like this. Now, what we are talking about, and some component will be absorbed also in both the cases. So these are the atomic planes in a crystal. Now from here on, X-rays are coming in of certain wavelength. So it may not happen automatically. This crystal will interact. Okay. So, so from this atomic plane, because at the end of the day, it is like a matter and a wave is incident. So basically, it will be scattered. So suppose there is another parallel beam, and it is being scattered. Now the condition of constructive interference of these waves is that those waves have to they should have same wavelength. They are already coming from same source, same wavelength. They should maintain a constant phase difference. Then they can make constructive interference. And because of constructive interference, intensity can grow rapidly. The idea is that if this angle, if I draw a normal here, if this angle is theta, and so this separation is d. D is the separation between atomic plane. Okay, separation between parallel planes. Now the condition of constructive interference is this much twice t sine of the angle of incidence is the sine theta and lambda. Lambda is the wavelength of the incident light. Theta, sine theta is the angle sine of the angle of the incidence. D is the separation. Okay, this is Bragg's law of X-ray diffraction. Two laws, conditions are there. These two angles should be equal. Okay, angle of incidence, angle of reflection, scattering should be equal. Almost like reflection will take place, and this is a condition of sustained interference. Now we're almost we're done with this. So you can see whatever I've told you, it is happening here. Okay, it's coming in, and they will make interference. Condition of sustained interference is there. Okay, this is the written form, the Bragg's law. So it's a father and son form. Okay, that is 2 of d sine theta equal to L lambda. Okay, so that thanks for this particular lecture. So next we'll be talking about semiconductors. Thank you.
You and me were meant to be in the great outdoors, forever free. You and me meant to be bird on a tree. I'm just sitting here, I got time, it's clear to see. From up here, the world seems small. We can sit together, it's so beautiful. You and me, we meant to be in the great outdoors, forever free. Sometimes you need to go and take a step back to see the truth.